Okay, so now we are going to look at formal notes for Chapter 2, Section 3. A graph with n vertices, no multiple edges or loops, is called a simple graph. So anything that doesn't have loops is connected, no multiple edges is a simple graph. A complete graph is a simple graph that has the most possible edges without multiple edges or loops. The number of edges in Kn is defined by the formula n times n minus 1 divided by 2. These are also called the triangular numbers, which is a series of numbers that has a pattern. If you are so interested, you can Google that and learn more about it, but you just need to know n times n minus 1 divided by 2. There are n minus 1 factorial Hamilton cycles in Kn. This is not that I am that this exclamation point does not mean that I'm wicked excited about math. I mean, I am wicked excited about math. I have many degrees in the subject. I love math. I love sharing my love with of math. But that exclamation point is actually a mathematical operation, not that I'm excited. And then there are n minus 1 factorial divided by 2 distinct Hamilton cycles in Kn. This exclamation point means factorial. So if we are looking at how to calculate it, 1 factorial is 1, 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, 4 factorial is 1 times 2 times 3 times 4 times 4. 5 factorial is 1 times 2 times 3 times 4 times 5, etc. So this is 1, 2, 3, 12, no, 24. No, yes, 24. This is 6, not 3. I can do... Okay, I have multiple degrees in mathematics. That means arithmetic and I don't get along. This is 24, and this is 120. No, it's 60. No, it's 120. All right, so now let's work on doing some fractions with this. So 6 factorial divided by 4 factorial. Now, we don't want to use a calculator because the ones in the quiz that I'm going to give you, you're not going to be able to use a calculator at all. So 6 factorial is 1 times 2 times 3 times 4 times 5 times 6 divided by 1 times 2 times 3 times 4. I can cancel those out. That becomes 1, and this just becomes 5 times 6, or 30. Now, I'm going to represent this differently because it's going to be really hard to write out 1 times 2 times 3 times 4 times all the way up to 13. So I'm going to represent this as 12 factorial times 13 divided by 12 factorial. This is a-okay to do because 12 factorial is 1 times 2 times 3 times ... times 11 times 12. Okay, so it's just we can just represent it, cancel that out, and we get 13. This one, not so easy. So we're going to break up this fraction because right now the 100 factorial is the common denominator. So we're going to go 101 factorial divided by 100 factorial, and then plus 102 factorial divided by 100 factorial. So this is just 101 plus, now 102 factorial is 100 factorial times 101 times 102. Now you can do this kind of manipulation always, because it's just multiplication. And it's divided by 100 factorial. That factors out, so that leaves me with 101 plus 101 times 102. Now I say without using a calculator, but where's my, why are you not in my, there we go. So this is 101 plus, which equals, so that is just some things. If you want to go over this some more, I don't really think you need to, but some students do struggle with this concept. Go ahead and look up factorials on a website called khanacademy.com. Search for factorials. I heart Khan Academy for learning math. They're pretty awesome. So I believe that is all the notes. So what you need to do here is just fill in this chart. Now the reason why we have the n minus 1 factorial for the number of Hamilton cycles, and we have n minus 1 factorial divided by 2 for distinct Hamilton cycles, is because, let me draw an example so we have something to go on. I'm going to erase that. I'm going to go ahead and draw a K4 down here. Because a K4 has 4 minus 1 factorial, or 3 factorial Hamilton cycles. And it has 4 minus 1 factorial divided by 2, which is 3 factorial divided by 2 distinct Hamilton cycles. So this equals 6, this equals 3. Now I'm going to show you the difference in these by doing it in a nice small example. I would do it in 3, but I don't think that 3 is enough to show you. So if I was going to find the Hamilton cycle A, C, D, B, A, I could also say that there's a Hamilton cycle A, B, D, C, A. So A, I'm going to change the color. A, B, D, C, A. These are the same cycle. Okay, so what this distinct Hamilton cycle does is takes out these, the backwards ones. So let's find all the rest. So that way there you guys can have at least one example of this. So A, B, C, D, A is also the same as A, D, C, B, A. Now, in deeper explorations in graph theory, these may not necessarily be the same because of something called directed graphs, where the direction matters, but we are using non-directed graphs. We will never get into directed graphs, but so as of right now, and for your purposes, the direction doesn't matter. So let's find the last two. We'll use yellow. A, C, B, D, A. So A, C, B, D, A is the same as A, D, B, C, A. So that divided by 2, the n minus 1 factorial divided by 2, eliminates the double counting. So what you just need to do here is using your calculator, you just need to fill in these numbers. So number of Hamilton cycles, number of distinct Hamilton cycles, just all the way through. I'm not going to collect this, but you're going to need it for the homework. And then homework for problem set 4. So hopefully that helps. Good luck.